Welcome to Mrs. Mahoney's podcast. This is our fourth and final one for our Unit 9. So we're at the top of page 13 and we are going to look at that stoichiometry of gases. We're not going to freak out with stoichiometry. We're going to just look at it again with an approach and really probably realize, you know what, it's not so bad the second time around. Okay, we're going to look at a first case that of only a gas to gas. Okay, a lot of times I say pay attention to the details. This is really, really important to pay attention to the details because there is a shortcut when we're going from gas to gas. The shortcut is I can just use the mole ratio is going to be the same. But the thing is, this only works with gases to gases. So let me just show you an example. Okay, first, what do we do with any stoichiometry? That doesn't change. Balance the equation. Oh wow, look at, here's that reaction again. Hydrogen plus nitrogen gives me ammonia. Okay, I just want you to watch something for a second, and I'm going to prove to you why the shortcut works. If I was just doing this normal, what do I have to do? Okay, 5.5 liters, what do I have to do to liters? I need to go to moles, have to go to moles. Well, it's at STP. What do I know? I know 1 mole is 22.4 liters. Okay, and this is 1 mole of what? Hydrogen. But what did it ask me? Just in stoichiometry, it asked for ammonia, so using your mole ratio. So I get out 2 moles of ammonia for every 3 moles of hydrogen using my mole ratio. But then it asked me for liters, okay, and it's at STP. Well, what do I know about any gas? 1 mole of ammonia is 22.4 liters. So hopefully you can see a little bit of the redundancy because I'm dividing by 24, but then I'm going back around and timesing it by 24. This is where that shortcut comes in. So what happens is I don't need these steps. So now you can quit watching and just participating of why this is that shortcut. We can use the mole ratio, but we're going to call it a volume ratio. So if I look at this, again, what am I starting with? 5.5 liters of hydrogen. So using this, instead of calling them moles, we're going to call them the liters. I know that I get 2 liters of ammonia for every 3 liters of hydrogen. So here's that same step right here. This is the only step, which is that mole ratio. So 5.5 times 2 divided by 3, I would get out 3 liters of ammonia. Now hopefully this you think back to our mole rocket lab. What do we figure out? You needed that 2-to-1 ratio. What was that? 2 parts hydrogen to 1 part oxygen. That was a volume ratio because you didn't have a whole mole of it, but the volume ratio is the same. So let's look at right here. So even though if it's not at STP, I could prove this too because what do I use? PV equals nRT, solve for moles, use my mole ratio, then I would have to go back and use the exact same numbers in PV equals nRT, everything would cancel. You're again doing too much work. So when I'm looking at this, as long as I'm going gas to gas, that's when the shortcut works. So I have 10 liters of oxygen, and I want to know how much water. Well, I get out 2 liters of water for every 1 liter of oxygen. 10 times 2, I would need 20 liters of water. Okay, I want you to do number 2. Looking at this, you guys, this will be one we'll kind of do tomorrow when we start. You can do number 2. That's liters to liters. Okay, let's look at number 3 and 4. This just looks a little bit different. And notice, this is at STP, and I'm going to use that fact again. Why is it a little different? I didn't give you liters. So that means I'm going to have to get to liters because it is still gas to gas. So it is still a gas to gas. Well, at STP, I know something. Remember, at STP, I know that 1 mole is 22.4 liters. So if I get this to moles, I can get it to volume. So let's just figure out 24.5 grams of ammonia. I need to get it to moles. How do I go grams to moles? Molar mass. 1 mole of NH3, 14 plus 3 is 17 grams. Now I've got it to moles. Okay, now you have two ways you could do this. I could either call it a mole ratio and then go to 22.4, or I can go to volume and then I use a volume ratio. Let's go to volume. So that means I would say 1 mole of NH3 is 22.4 liters. And then what would I do? I would say, oh wow, I didn't balance it. So now I'm going back up and I need to balance it. What is this saying? And this is NH3, that for every 2 liters of NH3, I need 1 liter of nitrogen. So 24.5 divided by 17 times 22.4 divided by 2, and 3 significant figures, I would get 16.1 liters of ammonia. Okay, if you wanted to do it the other way, I'll just write down here, what would that other way have looked like? Right here, I would have used the mole ratio. I would have just flipped these two. I would have said, okay, for every 2 moles of NH3, I need 1 mole of nitrogen. And then to get to liters, I could have said 1 mole of nitrogen is 22.4 liters. So if you look at mathematically, we're doing exactly the same thing. So it might just kind of be how you think of it and how you process it. This would have been the same. The reason I did this, you still would have had to get to moles. This is what would have been different. All that mattered is which step you did first. Either way is fine. Okay, number 4, I want you to do that. So you're going to have to synthesize. That means you're going to have to make hydrogen chloride. So what is that? Chlorine, that's a gas, plus hydrogen, that's a gas, to make hydrogen chloride gas. I'm going to let you balance it. I'm going to let you finish this. That's 75.3. Your answer should be 23.1 liters of chlorine. That's what your answer should be. Okay, and you're probably going, yes, this is easy, Mrs. Mahoney. Are they all this easy? Unfortunately, they can get a little trickier because let's face it, not everything we're going to look at is a gas to gas. So I want you to look on page 14, and we're going to do a couple of these, and I'll let you do a couple. Notice the difference, okay, if I'm reading these. What volume of chlorine gas is required to react with 0.5 moles of silver? Silver is a solid, no shortcuts. So if you go back up here, you have to do two things. You have to do stoichiometry and the ideal gas law. Now, which one you do first depends on what you are given. So if I look at this, to do the ideal gas law, let's list out what I know. Temperature, 17, because it's asking me for volume. I know I can do the ideal gas law. I'm automatically changing that. So that's 290 Kelvin. Okay, what do I know? I know pressure is 0.95 atmospheres. Okay, it's asking for volume. Well, it looks like right now I have another unknown because I don't know what my mole is. I know my R because it's 0.95. I'm going to use my 0.0821 because that's liters, atmosphere, mole, Kelvin. Problem is I have too many unknowns. So I'm going to have to do stoichiometry first to find my moles, and then I can use the ideal gas law. So I'm going to look at my balanced equation. I have 2 moles of silver for 2 moles of silver chloride. What did it give me? It gave me the 0.5 moles of silver. So I can use this to find this moles of my chlorine gas using just the mole ratio. So I know that I need 1 mole of chlorine for every 2 moles of silver. So 0.5 divided by 2, I only need 0.25, and I'll only have 2 sig figs, so 0.25 moles of chlorine. So right here, this is how I figured out this moles. So now look at, now I can do an ideal gas law. PV equals nRT. So remember, PV equals nRT. So what is my pressure? 0.950 is my pressure. Volume's what I'm looking for. N, I just found 0.25. My R's 0.0821. My temperature was 290. So multiply these together, divide it by 0.950, and you get X. My volume is 6.3 liters of the chlorine gas. Okay, look at number 2. Pretty much exactly the same thing that I'm going to be doing. It's a heck of an equation. I want you to work this one, but here, I'll give you a shortcut. Let's balance it together. This is a liquid. This is octane. This is your gasoline. Burns in oxygen. What do I get out? It's combustion. Carbon dioxide as a gas. Water usually comes off gas or a liquid. It really doesn't matter because that's not what we're looking at in this one. Okay, this one to balance, it's not going to work because this would be a 9. You're going to have to come back and double. So what does that mean? I'm going to have a 16 carbon dioxides, 18 waters, 32 plus 18, that's 50. You need 25 oxygens, 25 moles of oxygen. Okay, so now looking at this, now I can solve for this because what do I have to do? So look at this. First I'm going to have to figure out moles of my octane. So grams, I'll get you started here. This is how many moles. The molar mass is 114.2 grams. And this is moles of octane. And then you ask, where am I going? I want to go to carbon dioxide, so it's 16 moles of carbon dioxide for every 2 moles of your octane. Okay, so get this answer, then take these numbers, plug them into the ideal gas law. Your answer should be 152 liters of carbon dioxide. So notice in both of these, we had to do stoichiometry first because it gave us a non-gas. We had to do the stoichiometry to find the moles to be able to use the ideal gas law. Okay, so let's compare that to the next 2 problems. Okay, first thing again, we have to balance the equation. 2 to 2 to 3. Okay, if I read this, what mass potassium chloride, that's a solid, would be needed to produce 11.2 liters of oxygen? So what do I know? I have a volume of oxygen. What else do I have? I have a pressure. This is in kPa's. I have a temperature, which is 37 degrees plus 273. That's at 310 Kelvin. Okay, what else do I know? Well, I know an R because it's kPa's, 8.31. Well, look, I can solve for moles first. I know that because that's my only missing variable. I can do this math. I can solve for moles first. So I'm going to use, in this case, PV equals nR2. So pressure times my volume, moles, over 8.31 times my temperature. Again, this says equals. So this 50 times 11.2 needs to be divided by 8.31 times the 310, divided by that whole quantity. So I do all of that, and what do I find out? That I have 0.217 moles of oxygen. So I had to do the gas law first. Now I can go back and do some stoichiometry. So moles of oxygen, but it asks for potassium chlorate. So for every 3 moles of oxygen, what do I know? I need 2 moles of potassium chlorate. Okay, it didn't ask for moles, it asked for grams. So to go to grams, molar mass of potassium chlorate, so 1 potassium plus a chlorine plus 3 oxygens, is 122.6 grams. So I'm going to take this mole I found times 2 divided by 3 times 122.6. To produce this, I would have to have 17.7 grams of my potassium chlorate. So that many grams is needed to produce my 11.2 liters of oxygen. So notice sometimes we're doing the same thing, it's just really the order that you do it is what matters. Okay, so again, I'm going to leave this for you. I'll get you started on a couple things because when I'm reading this, when sodium reacts with excess water, how many grams of sodium? This is what I'm looking for. How many grams? That's a solid. When I'm looking for a solid, that tells me I'm going to have to do the gas law first. Okay, are required to produce. So look at what I know. I have a volume, and it's hydrogen gas. Oh my gosh, 3 magic words. They were collected over water. Oh, there's the two magic words. But you know what else? Look at this. Partial pressure of water I was given. This is just when you have to do that pressure correction. Pressure correction. I just want the pressure of hydrogen. So the pressure of hydrogen is the total pressure minus the water vapor. So the total pressure, and the number I'll actually use in my ideal gas law, is 640 millimeters of mercury. Okay, what else do I know? I know a temperature. My temperature is 30 degrees plus 273, so my temperature is 303 Kelvin. What else do I know? My R, because it's millimeters of mercury, I'm going to use 62.4 because that's millimeters of mercury, liters, mole, Kelvin. So that's how I know this. So what I'm going to have to do the ideal gas law first, then use your moles, and then you make sure that you've got everything balanced. You're going to use your moles. So your equation's balanced. You're going to have to do the ideal gas law first, find your moles, then you use your mole ratio, get to grams then of sodium. So doing all that, your answer should be 10.1 grams of sodium is necessary. That should be your answer. So kind of go through that to make sure you get the answer. I'm going to start with that tomorrow, looking through that, asking if you have questions, and then we'll just do some more practicing on gas stoichiometry. See you tomorrow.